Today's video is essentially a quick 101 introductory to terrestrial laser scanning, what it is, why it's used, and most importantly, how it's done. Because we're just covering the fundamentals, this is designed for those new to terrestrial scanning. Maybe you've used it a few times and just want a couple tips and tricks, or maybe you've never used it before, but you've seen it or heard about it and are just curious. Let's get after it. While technically there are many forms of 3D laser scanning that take place terrestrially on the Earth, the term terrestrial laser scanning, or TLS, is often reserved for 3D laser or LiDAR scanning using tripod-mounted static scanners, and specifically those 3D laser scanners that set up arbitrarily and take panorama scans that are stitched together using overlapping scans or common targets. Total stations that can scan as a secondary function are in a class of their own and not what we are focusing on today. Essentially, a terrestrial laser scanner is placed on a mounting device, typically a tripod, that holds it in a fixed position while the scanner rotates, emitting hundreds of thousands or millions of lasers or distance measurements every second. Every time a laser bounces off an object and returns to the scanner calculates how far that laser traveled and the horizontal and vertical angle it was emitted at. It uses that information to calculate a point in 3D space relative to the scanner that represents the location of whatever object that individual laser reflected off of. As these millions of points are combined, we start to get a virtual representation of the environment that surrounds the scanner, made up of a multitude of individual points that all have three-dimensional coordinate values. These points can be so dense that they can appear to create an uninterrupted surface. We call this collection of points a point cloud. Because we often want our point cloud to extend beyond what can be seen from a single scan position, we then pick up our scanner and move it to a new nearby location and repeat the process. This is done as many times as is needed to map the environment we want data for. Those individual scans are aligned to each other using a process that is called registration. An approximate registration of one scan to another is usually performed in the field within the scanner software and then further refined in the office after the data is transferred onto a processing computer, either locally or in the cloud. The process of registration is typically done one of two ways, or a combination of the two, either via cloud-to-cloud registration or target-based registration. With cloud-to-cloud registration, the software looks at the points captured from one scan and the points captured from a subsequent nearby scan and shifts and rotates one scan to best fit the other. This method requires overlapping points of the nearby scans you wish to align to each other. As the name implies, target-based registration uses distinct targets placed in the area of scan captured during data acquisition, oftentimes black and white checkerboard targets whose locations have been measured with a total station. When 3 or more targets are scanned from each scan position, we can essentially perform a resection for every single scan, which resolves the position and orientation of each scan position. This method can be used on its own or in conjunction with cloud-to-cloud registration. We use terrestrial laser scanning to capture point clouds. The specific use of point clouds can be varied, but essentially we use them as a means to extract geospatial information. It could be a ground surface for a topographic survey, it could be floor plans of a house, it could be a 3D model of a 2 million square foot airport. The why we specifically choose terrestrial laser scanning over other methods of 3D scanning can be a bit more nuanced. Generally, it comes down to accuracy, data density, range capabilities, reliability, and portability. For simplicity's sake, let's lump 3D scanning into 4 groups: SLAM scanning, vehicle-mounted mobile scanning, aerial scanning, and terrestrial scanning. SLAM, mobile laser scanning, and aerial laser scanning are all quite a bit faster than terrestrial scanning. They capture their point clouds from a moving platform that doesn't need to iteratively stop to acquire data. This means they can capture data much quicker, but doing so from a moving platform means you generally sacrifice accuracy and, in some cases, portability. If you're using mobile scanning or aerial LiDAR, you're going to have scan shadows in areas you typically wouldn't when using terrestrial or SLAM scanning. With both of those capture methods, you're at the mercy of where you can move and operate the platform. You can't really fly a drone or drive a vehicle through the front door of a building after you've captured the exterior to start mapping the interior. Now, there are some exceptions to this rule, such as Emison's STX, that can be operated from the air, mounted on a vehicle, or used as a handheld SLAM scanner. When using SLAM, you can usually fit it in all the same tight spots a terrestrial scanner can get into, and even more so in some cases. But generally, accuracy, point density, precision, reliability, and point cloud fidelity take a hit. When it comes to the why of using a terrestrial scanner over a total station, it comes down to data density. You can scan the facade of a building in under a minute, made up of millions of points. When using a total station, you would be lucky to capture 10 discrete points per minute. An argument could be made that when measuring discrete points with a total station, you save a lot of time in the office when it comes to feature extraction, but depending on the use of the data, terrestrial scanning can still be much quicker overall. If you need to locate an as-built of a single concrete pedestal, you may as well use a total station. It will be much faster. If you need an as-built of 200,000 square feet of infrastructure, it's time to switch over to 3D scanning. And when you do so, you get the benefit of mapping the entirety of the environment. If you miss features with a total station, you would need to remobilize to site to capture what was missed. When you scan, you have a high level of control in the office of what you wish to extract from the data set. Let's get into some tips and tricks about how one can perform a thorough and reliable capture using terrestrial laser scanning. The first thing I do when I arrive on a site that I'm going to scan is do a site walk and get my eyes on every inch of the area of interest. As I'm walking the site, I'm picturing where I'll leapfrog my scan positions. I'm looking for access issues such as locked doors. I'm looking for foreign objects that will affect the scan data of critical areas such as dirt and debris on a floor that requires a floor flatness survey, and I'm making sure I'm communicating with my site contact about exactly what my plans are for the duration of my time on site. A little tip, if you're scanning for a floor flatness survey, bring a battery operated leaf blower with you. Trying to filter out dirt, dust, and debris from actual floor in the scan data can be near impossible. It never hurts to request all doors be unlocked prior to arrival on site, but 90% of the time that doesn't happen, even if the site contact ensured us it had. That's why it's a great idea to check every doorknob or gate you need to gain entry to and insist that now is the time that any access issues be resolved. There are few things that can slow production down more than scanning your way up to a room and finding out it's locked and then having to chase down the set of keys that open it. Communication with your site contact can be vitally important to the success of your data acquisition. And we've found quite often that our site contact usually isn't the best or only person required for gaining access to obscure locations, especially in industrial settings. It's not uncommon that you may need to go through 3 or 4 separate people to gain access to every room required. Specialized areas in a building like utility rooms for fire suppression, high voltage rooms, finance and communication offices are often controlled by different departments, and without proper planning around this, you could nosedive into a logistical nightmare. I like to turn on every single light in the area of interest I'm scanning as I do my site walk. It helps from a safety perspective when I come back through there, but also for the panorama images and subsequently the RGB values of the point cloud. If the area you're scanning doesn't have sufficient light, you may need to use a battery operated floodlight if imagery or colorization is important to the client. When doing above ceiling scanning, we will often strap an LED headlamp to the front of the scanner. It usually works fairly well for small tight spaces. If the project requires survey control, I will perform a second site walk after getting the ball rolling on any access issues found. During this walk, I will demarcate as many of the control points as possible, often working hand in hand with the other scanning technicians with me so they know exactly where the control points are that they will need to tie into. If your data capture team is split up into a surveyor and scanning technicians, it's much easier to have all control points demarcated before the scanning technicians start their data capture. Otherwise, they might have to double back to tie in control that was placed in areas they had already scanned once the control points finally get established. And always carry at least a few door steps with you, ideally the type that can be used under the door or in the door frame. You don't want to start scanning your way through a door and have it slowly closing on you because you have it jerry-rigged with some scrap piece of wood, or have to hunt down something heavy enough to prop it open every time you come to a new door. It's important to consider how long you intend to be scanning for that day and weigh that against how many batteries you have available on hand for your scanner. For example, if I know I will be scanning more or less nonstop for 8 hours and I have 4 batteries on hand and 2 batteries will last me about 3 hours of scanning, if I don't bring the battery charger with me, I won't be able to complete my desired 8 hours of scanning. The fix for this very common situation is to bring the battery charger for your scanner's batteries with you, find a power source, ideally centrally located to the area you're working in, and start charging your depleted batteries as soon as your first set of batteries die. If you're working in an area without easy power access, but in a secure location, you can use a portable 120 volt power bank. If your scanner uses a tablet or phone to operate it, it's also a really good idea to keep an external battery bank with you to charge your tablet as you scan. I can usually get about 5 to 6 hours of nonstop scanning out of an iPad Pro when running Field 360. Not enough for a full day, so I just keep a 20,000 milliamp hour battery in my vest pocket plugged into the iPad while I work. And a little tip when doing this, use a high quality cord to ensure the battery bank can keep up with the power consumption of the iPad, ideally one capable of 30 watts or more. Data management on the scanner is also important to have sorted out before you start scanning. It can really slow things down if you reach the capacity of your scanner's hard drive in the middle of a job and have to scramble to find another external hard drive or start transferring data off the one you have. Before I start my day, I know approximately how large of a file size a raw scan will be depending on what scanner I'm using and the point density and imagery settings I'm using. I also know approximately how many scans I intend to capture for the day. Using some simple multiplication, we can calculate approximately how much storage we'll need to complete that day's work. For example, when using Regal's VZ600i, a single scan at a 6mm density with imagery is about 1 gigabyte of data. If I know I want to perform 500 scans that day, which is typical of a full 10-hour production day with a VZ, I'll need half a terabyte of storage available to me on the CF Express card. If I have a full week of scanning planned, it really doesn't hurt to have a few extra terabytes of CF Express cards in hand. They're not that expensive in the grand scheme of things. Typically, when we use a terrestrial laser scanner, we rely on overlapping points from one scan to other nearby scans and cloud-to-cloud registration to align the individual scan positions together. Because of this, the amount of overlap from one scan to another is extremely important. For example, if I have 2 scans inside of a room captured right beside each other, both of those scans will capture the walls, the roof, the floor. The registration software of our scanners will look at those common features and use them to best fit the 2 point clouds to one another, which the software will be able to do very accurately because there's a high percentage of overlapping points between the 2 scans with great geometric diversity. Conversely, if those 2 scans were separated by the threshold of a door that led into the room, there would be very little overlapping points between the 2 scans. It's important to not think of terrestrial scanning in the same way we think of a total station. Line of sight between the scan positions really doesn't mean much in terms of registering the 2 scans to each other. It comes down to the common features each scan has line of sight to. When I have a terrestrial laser scanner set up and capturing data, I like to take a mental picture of everything within its line of sight at its operational range and use that to imagine what features would be common when I move the scanner to the next setup. If you're scanning your way through the threshold of a door, you may find it advantageous to have one scan a few meters on one side of the threshold, one right in the threshold, and one a few meters on the other side of the threshold. When scanning around an exterior corner, I prefer to use 3 scans to make my way around that corner. 2 on an extension of each wall and 1 offset to the actual corner. When in doubt, add an extra scan. An extra minute or 2 in the field can save a lot of headaches in the office later when it comes time to process the data. And try not to hum and haw too much about your next scan placement. As the scanner is working its way through the current scan, you should have your next scan position already picked out. If you make it a habit of wasting 15 or 30 seconds on every scan, getting your bearings after your scan is finished, and only then start to choose your next scan position, that can really add up over a 300 scan day. I like to use the acronym ABS, always be scanning. If you're not quite sure if you really need that filler scan, and start peeking around to see if it adds network strength or removes any scan shadows, just take the scan. Ideally, your scanner is either capturing data or moving to a new scan position. You're rarely going to degrade your final product by adding in an extra scan here or there, but missing one might certainly do just that. And ideally, we want distinct geometry in each axis to really tie down the registration. Imagine if we were scanning out in the middle of an open parking lot. We could take 2 scans just a few meters apart, and the registration software would have little idea of how to align those in the X and Y axis. It would have the information from the IMU and other navigational sensors depending on the scanner, but the 2 scans would basically look like 2 flat planes sliding on top of each other without any features perpendicular to the Z-axis to help nail down their position horizontally. When we run through this example with an RTC 360 and bring the data into Register 360 and hover over the strength readout of the links created, it gives us a nice little breakdown of the alignment in each axis. Even though the overlap percentage and error looks okay, we can see that the pairwise registration between these scans is extremely weak in the X and Y axis. When you're in the field and planning your scan network, this concept is important to understand. If you're in a situation lacking geometric diversity, like that parking lot example, there's a good chance cloud-to-cloud registration won't be enough to accurately resolve how each scan position aligns to each other. As we just alluded, terrestrial scanners often integrate in IMU, specific cameras, compasses, and sometimes GNSS antennas to assist the field registration software by helping it track where we've moved the scanner relative to the previous scan position. This gives the registration algorithm an approximate location and orientation relative to the previous scans is a starting point for the cloud-to-cloud registration. It's a good idea to move your scanner deliberately from one position to another. Try not to pick it up, stroll around until you think you found a good scan position. If you wander too much, you increase the possibility of confusing the internal navigation system of the scanner, which could cause issues for the field registration. Not that those issues can't be fixed if the field registration failed, but being mindful of this can save time and effort needed to fix unnecessary issues. While you're building up your 3D environment from scans you're capturing, it's important to not only be cognizant of how one scan registers to other nearby scans, but also the geometry of the network of scans you're creating. For any of you surveyors out there, your network of scan positions isn't too much unlike a traverse. In the same way you want to close a traverse to distribute air, you want to close out your network of scans. And for any surveyors familiar with least squares adjusted traversing, there is also great benefit from closing your network in as many ways as possible. If you're scanning a building with 4 entrances, it would be preferable to join your exterior scans with your interior scans by scanning your way through each one of those entrances. And if you're scanning a building with multiple floors, the same applies if there are multiple stairwells. I made a video not too long ago where I measured how the density of control points affected the overall relative accuracy of a scan network. To summarize the findings of those tests, point clouds that had good overlap between all scan positions and there were multiple closing scan legs were relatively quite accurate with and without control. As I started breaking apart the network by removing those closing legs in stairwells or through doorways, the accuracy significantly decreased until I started closing out those spur legs with control points. Again, very much like a traverse from a total station. Just like you can close out a traverse onto itself, you can close it out to a known control point. The same goes with a terrestrial scan network. A long linear string of scans is prone to wobbling at either end until you start adding survey control points along that linear network. If you had to create an example of the worst possible scan network geometry, it would be a linear string of scans with little overlap and poor geometric diversity. Imagine a tunnel. If you had to think of an example of a strong scan network, it would be a square polygon of scans with strong overlap, great geometric diversity, and an abundance of triangulated links between scan positions. When you do your site walk, you should be planning how you're going to close your scan network. This will vary from site to site, but the location and quantity of survey control needed will be directly influenced by your scan network geometry and the desired accuracy of your final point cloud. Sometimes you may not need any external survey control if georeferencing isn't required and strong network geometry is possible. Sometimes you may need quite a bit. However, keep in mind if you don't have any external control points, you may find it difficult to reliably prove the accuracy of your dataset, as using the metrics provided from the registration software alone are problematic for a variety of reasons beyond the scope of this video. I recommend checking out my videos on how control affects point cloud accuracy and my one-dimensional method of measuring point cloud accuracy video for more information on that topic. And this leads us to the next topic, scanning targets. Different scanning manufacturers use different scan targets to demarcate a control point in the scan data. For example, Leica's RTC360 uses checkerboard or spherical targets. When the scan data is processed, Leica uses the contrasting intensity values of those black and white targets or the shape of the spherical targets to define the location of the target in the point cloud. Regal opts to use retroreflective targets that can come in a variety of shapes, with the most common being flat discs or cylinders. These have to be fine scanned after the initial panorama scan. The targets we scan typically have a northing, easting, and elevation coordinate value applied to it from either a total station or GNSS. When we're in the field, we want to make sure we scan the target as best we can so the processing software can define the center of those targets as best it can. If you're using a scanner that works with black and white targets, you should be close and perpendicular to that target, ideally within 3 to 5 meters. This ensures the registration algorithm has an optimal density of points on that target to precisely define its center. If you're using retroreflective targets and your scanner does a specific target scan for each target in the field, you can usually get away with scanning it from a further distance because that target scan will often use a much higher point density for that specific target scan. The exact distance will depend on the density of the target scan and the size of the target you're scanning. Flat targets, whether checkerboard or retroreflector, that are pointed perpendicular to the scanner at a distance that provides good point density on those targets, can very accurately define the center of target in the point cloud. Cylindrical or spherical targets often define the center of target in the point cloud less accurately, but do have a couple of advantages. In the case of scanners that don't have a specific additional target scan like the RTC, you can scan those spheres at a further distance because you're relying on the shape of the sphere as defined by the point cloud to determine the center of target, not contrasting intensity values. Again, the actual distance will vary depending on the size of the sphere used and the point density of your scanner. You can also scan them from any direction, which means if you're repeatedly scanning the same control point from numerous scan positions, you don't need to walk back to your target and rotate it as you move to each new scan position. This is handy when doing target-based registration. The same advantage applies to cylindrical targets, with the caveat being that as you scan cylindrical targets from a steep overhead angle, the accuracy will start to suffer. Hands down, my favorite way to scan targets is a Rothbucher mini tripod and the one point fits all paddle. I have a full video dedicated to this topic, so if you're not already familiar with these, I would recommend giving it a watch. For larger projects, it can be helpful to segment scans into specific jobs while capturing data in the field. For example, when scanning a larger project using Leica's RTC 360, you may start to experience significant lag on your tablet running the field capture software that can affect productivity as your scan starts to grow. Or when scanning a building with multiple floors, some field capture software packages only let you view your scan positions in a 2D top-down view and don't have any way to separate the scans by elevation, which can make it confusing as to where you've already scanned on the floor you are currently working on. Or perhaps you have multiple people scanning simultaneously on a single project. In these scenarios, it's helpful to have a clear plan as to how exactly you want to segment a project. Perhaps it means a new job every floor with the connecting scans via stairwells belonging to the lower floor. Or perhaps scan technician A will scan the exterior of the building and scan technician B will scan the interior. Whatever method you choose, it's important to plan ahead, and if working in a team, make sure the plan is well communicated. It can be handy to use control points as a delineation line. This way, both data sets are tied into common control points. The last thing you want to have happen is to find out neither person performed the connecting scans between jobs because they were under the impression the other person was going to do so. Scan shadow is the term used to describe an area of missing points due to a blocked line of sight in a 3D scan. When you start a 360-degree or panorama scan on a terrestrial laser scanner, it rotates horizontally and captures 360 degrees of points. There will be a cone of occlusion below the scanner where it cannot see, and for scanners that cannot measure points overhead, such as most Regal terrestrial scanners, there will be an overhead cone of occlusion as well. Beyond that, when our scanner emits a laser, those lasers cannot pass through an opaque object, just like any other source of light. If we imagine the 3D scanner as a light source, shadows would be cast on the far side of all objects that block its light rays. Just like they block visible light, the objects block the lasers emitted from the scanner that are used to take distance measurements and thus create shadows in the point cloud. These shadows are iteratively eliminated as we leapfrog our scanner from one position to another. We already talked about how the scanning technician needs to be mindful of overlap when choosing each scan position, but they must also weigh how their choice of scan position location affects the creation and elimination of scan shadowing. Moving the scanner 1 foot to the left or right may mean the difference between capturing critical infrastructure or missing it. You'll almost certainly have some level of scan shadows remaining in your final data set. It's very difficult to completely eliminate them with terrestrial scanning, but you don't want scan shadows over important areas of interest. For example, if you've been hired to scan a building and the client wants the fire suppression system extracted from the point cloud, you would want to identify all visible bends in the water supply piping and ensure that those areas have good coverage. If there is some shadowing or missing data along a straight run of pipe between two elbows, the digitization team can work with that. But if there is an elbow or deflection missing, it could be near impossible for them to interpret the true location of that pipe run given the missing data. Also, try to remember we aren't restricted to only moving our scanners horizontally. There are plenty of situations where it will be beneficial to lower your tripod. Most scanning tripods have a quick release button on the legs that allow you to spread them to get scans under obstructions. And extendable tripods come in a variety of shapes and sizes. If you're doing above ceiling work, These will allow you to crank your scanner up to get above ceiling panels. When using an extendable tripod, I highly recommend pairing it with a tripod dolly. And when the scanner starts capturing data, try to get out of its way. You being in the point cloud and imagery isn't the end of the world if there's nowhere you can hide from the scanner, but it's more noise in the data. You can add to scan shadowing, and if the client wants a clean data set, it adds time on the back end. In my experience, it's usually not the scan tech that's the issue, but if the job requires a chaperone for safety or security reasons, more often than not, you'll see them in every single scan. If you're working with other people, try to communicate where they should or shouldn't be during data acquisition. And if it's possible, capture data when there are as few people on site as possible. This may mean working during evenings or weekends, but in my experience, there can be a huge difference in productivity and quality of data when capturing a site that isn't full of people. Most terrestrial laser scanners give you the option to adjust the point density of the scans you're capturing, and it will often be expressed as a point spacing at a specified distance. For example, the medium density setting of an RTC 360 gives a point spacing of 6 millimeters at 10 meters. This means the measured points from a single scan will be 6 meters apart on objects that are 10 meters away and tangential to the scanner. With that same 6/10 setting, the points would be separated by only 3 millimeters on objects 5 meters away and 12 millimeters on objects 20 meters away, because point spacing versus distance from the scanner follows a linear relationship. Using a less dense setting such as 12 millimeters versus 6 millimeters allows for faster scan times and a smaller raw data file size, but you obviously get less dense point coverage on the objects you're scanning. When trying to choose the best point density setting for your project, you should weigh the desired point density of your final point cloud, the distance at which you're scanning your objects of interest, the amount of overlap between scans, the shape and intricacy of what you're scanning, and the angle of incidence of the objects you're scanning. We can increase the density of our point clouds in 3 different ways: by adjusting the scan density setting in the scanner, by moving the scanner closer or further away from the object we wish to map, or by adding overlapping scans. If your client requires a final point density of at least 6 millimeters and you're scanning a wall that's about 10 meters away, at first glance it would appear as if you should set your scanner to a 6 millimeter density setting. However, we must consider that the wall being captured is being done so not by a single scan, but by multiple scans to the left and right of that scan. And if we're doing 2 rows of scans, or if we're scanning inside of a room, there will often be a lot more than a single scan of data covering every surface. In that example, you could save significant time in the field and file size by switching to a 12 millimeter density and still retain sufficient point density in the final product. Now, using that same example, if above that wall we had a roof that needed mapping, because it's not perpendicular to the scanner, the point density would be much less at the same distance. The same number of points that covered a, let's say, 1 by 1 meter square tangential to the scanner now have to cover a much larger area on that roof, because that roof is not tangential or perpendicular and instead slanted away from the scanner. The same goes with round objects. When we scan a cylinder or sphere, the part of that object will have the highest density of points tangential to the scanner and then decrease as the angle of incidence increases. Obviously, the math starts to get too complex to start running calculations in your head at every new scan position, so it's always wise to err on the side of caution and give yourself some buffer when choosing a point density setting. As a general rule of thumb, if I'm scanning my way through a building in smaller rooms and hallways, a 12 to 14 millimeter point density is usually plenty. If I'm in a wide open interior space with tall roofs like a warehouse or working outdoors, I'll use a 6 millimeter density. And if the roof of that warehouse is, say, 20 to 30 meters high with intricate girder structure and small diameter piping and conduit, I may want to increase my point density further. The size and shape of what you're scanning has a very strong relationship between point density and how accurately you can digitize it. A point spacing of 15 millimeters won't really matter much on the side of a wall, but 15 millimeter point density on 1-inch conduit is almost useless. There are a few considerations one must make when choosing which distance to scan beyond point density. Accuracy and the distance at which something was scanned are directly correlated. The further away something is scanned, the less accurate those points will be. To what extent depends on the scanner being used. If we look at the spec sheet of Leica's RTC 360, it shows a 3D point accuracy of 1.9 millimeters at 10 meters, 2.9 millimeters at 20 meters, and 5.3 millimeters at 40 meters. As you can see, it degrades pretty quickly as we start pushing out our capture distances. Now, some scanners are purpose-built for longer range scanning and are less affected by distance, but the relationship still holds true. And beyond the accuracy consideration, we must also think about beam divergence. As a laser leaves the scanner, its footprint or the diameter of its beam starts off small, but grows in a linear relationship depending on how far it travels. How much it grows changes from scanner to scanner, but continuing with the Leica RTC 360 example, it has a beam divergence of 0.5 millirad and a beam diameter at the front window of 6 millimeters. This means when scanning an object 5 meters away, the laser used to make the measurement has a diameter of 8.5 millimeters. But at a distance of 40 meters, that footprint grows from 8.5 millimeters to 26 millimeters. If you're trying to define small complex features, having a footprint of over an inch could be problematic. If you're mapping a flat surface, it should have little effect. This is all to say there are numerous advantages to scanning objects closer rather than further away. Of course, this won't always be possible, but if it is, it usually makes sense to do so. For most terrestrial laser scanners, you have the option to take imagery with your scan data acquisition, either using internal cameras built into the scanner or an external camera attached to it. A series of pictures are taken, usually immediately after the scan data capture, and those images are stitched together to create a panorama image. Those images can be aligned and embedded into the processed point cloud to allow users of the data to overlay the images and the point cloud, which helps people that have never been on site use the imagery to make better sense of what the point cloud represents. The images are also used to apply RGB values to each point in the process point cloud, again giving better real-world context of the point cloud. Because images are often taken after scan data capture, this process takes additional time in the field, and quite often, the amount of time added can be significant, as much as double the time spent capturing the scan data. Because of this, choosing when images are required and when they are not is an important choice to make, one often dictated by either how the data will be used or client request. In some situations, you can mix and match. For example, let's say you're running a string of connecting scans between two distinct areas of interest. For these joining scans, data isn't required by the client, and instead you're adding the scans to improve network geometry. You can save time on these scans by reducing point density and not taking images. Time saved that can be spent more productively in other areas of your site. We covered how cloud-to-cloud registration works and briefly brought up target-based registration, but let's explore that option a little bit more. Target-based registration is primarily reserved for situations where there isn't enough distinct geometry for cloud-to-cloud registration to work effectively. When we use the term target-based registration, we usually aren't talking about adding 20 control points over 200,000 square feet to georeference it or help the cloud-to-cloud registration a bit in key areas. We're talking about using 3 or more targets for every single scan position and essentially performing a resection of the scanner using those 3 targets whose coordinates have often been defined by a total station or using GNSS. The registration defines the center of the targets in the scanner's own coordinate system, then looks at the surveyed coordinates of the center of those targets and shifts and rotates the scan targets to best fit the surveyed control coordinates. This defines a new position and orientation for the scanner inside the surveyed coordinate system from which all the measured points in the scan are referenced to. The advantage of target-based registration is that it lets you scan in areas without distinct geometry, which wouldn't be possible with terrestrial scanning unless you were using a scanning total station that you can set up and orient using control points like any other total station. The disadvantage of target-based registration is that it takes much longer to scan this way. You need a heap of control points and someone constantly surveying and moving targets to keep up with the scanner. An argument could be made that target-based registration is typically going to be less accurate as well. You're relying on how well the targets were surveyed and how well the registration software can define the center of each target. Of course, this depends on many factors, and if you're in a situation where the geometry was sufficient to allow for cloud-to-cloud registration, it would make little sense to start using target-based registration in the first place. It should be noted both methods can be used in conjunction with each other or on their own. An often overlooked task when 3D scanning is taking field notes of your scan capture. Field notes are hard-coded into the daily workflow of almost every surveyor, but for some reason that habit didn't carry over into the scanning industry. The main purpose of field notes are to bridge the gap between the scan technician's first-hand knowledge of how the scan was performed in the field and any issues that arose, and the person that needs to make sense of all this raw scan data to register it in the office. Information on how individual scan jobs connect to abutting jobs, which scan positions faced issues while capturing data, do any scans contain highly reflective surfaces such as mirrors, are all examples of metadata about that scan that would be valuable information to the person registering the data. Small things in the field that take just a moment to note down can save a lot of headache in the office when it comes time to connecting scans together, removing bad scans that are missing data, or hunting down which scans introduce reflected surfaces into the compiled point cloud. Data transfer can play a substantial role when we start dealing with terabytes of data captured from a single scanner in just a few days. If you're out in the field on a week-long project, you could quite easily capture hundreds of gigabytes of raw data every single day. Some companies prefer to mail physical hard drives back to the office for processing, and in some circumstances, this is the only realistic way to transfer data when you're capturing massive data sets every single day and are constantly on the move on mobile jobs. Others make use of file sharing platforms like OneDrive or Dropbox and send the raw data back to the office via the cloud. For those taking this approach, there are a couple things you can do to optimize your data transfer. Internet speed is always a consideration when taking this route. It can be beneficial to use a 5G MiFi or hotspot device with an unlimited data plan compared to relying on hotel Wi-Fi connections. This also allows you to start uploading data directly in the field before even getting back to your hotel if needed. Another tip if using OneDrive or Dropbox is always obviously zip your files, but also don't upload your data via the web browser. Instead, download their desktop app and sync your files that way. When you do this, you can lose internet connection or put your computer to sleep, and once you turn it back on or connect to the internet, your upload should resume where it had paused previously. And that about wraps it up. A quick and easy video this week. If you have any advice or tips of your own that you want to add, by all means, please do so in the comments. I'm sure there's some great info out there floating around that I missed and that I would like to hear myself. Thank you all for watching, and as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time.